Okay, so last time we proved the recursion theorem. I'm not going to restate it. The point of the recursion theorem was that in practice, in mathematical practice, we use recursive definitions a lot, and recursion theorem roughly stated that those recursive definitions make sense, okay? So when you try to define a function with some recursion, the recursion theorem says that those functions actually exist. Okay, and I proved a simple version. I told you there are variants. Indeed, today we're going to use one of those variants to define arithmetic operations. If you are really interested in the specific statement that allows us to define these arithmetic operations, you can take a look at the supplementary textbook I put in the syllabus, namely Yak's book, Introduction to Set Theory. So today we're going to define arithmetic operations on natural numbers, and then we're going to prove some basic properties. So by recursion, define a binary operation plus on the set of natural numbers. A binary operation on the set of natural numbers means that this is from n cross n to n, okay, by the following. So this is a binary operation, so it has two inputs, okay, and I'm doing recursion on the second input, okay. So in order to do recursion, I need to give you some kind of base point, like base information. For the specific case, you're going to do this. And the other cases are supposed to be, like the values at the other case, are supposed to be derived from that recursively. So I'm telling you that plus of m0 is m, okay? So this plus is the usual plus, it's the addition, but I'm going to write it in this notation for now. So m plus 0 is m for all m. And m plus the successor of some number is defined by recursion via the value of m plus n. So the value of m plus successor of n is defined by the value of m plus n. We take this guy and we take its successor. Okay? So this is supposed to be that f in the statement of the recursion theorem. Okay? So we define addition like this. Now, why does there exist such a binary operation by a variant of recursion theorem? Recursion theorem, such an operation exists. Indeed, such a unique operation exists, okay? Indeed, let me tell you how you can do this. So this is supposed to be a parenthetical remark. So you should prove that for any natural number m, there exists a unique function f of m from natural numbers to natural numbers such that f sub m of 0 is m and f sub m of successor of n is successor of f sub m of n, okay? So such a function exists for all m. You can prove this either by recursion theorem or by induction. I may show you why this exists at the end. Let me assign this as an exercise. show that this is true via induction. Show via induction that this claim is true, okay? So I'm claiming something about natural numbers, that for all natural numbers m something happens. Show via induction that this exists. You don't actually need recursion theorem for this specific claim, okay? So you can prove this by induction, by some work. So it's like this operation is supposed to be addition by m, okay? So this function I called f sub m is addition by m. When you add m to 0, you get m. And when you add m to successor of some natural number, you get the successor of the natural number which is obtained by adding m to n. So show that such functions exist. We then define the addition operation on the set of natural numbers to be the following set. So this is supposed to be a binary operation on natural numbers. So it's supposed to be a function from n cross n to n. In particular, it's supposed to be a relation from n cross n to n. So it's a subset of that. So I take all the pairs m and p such that f sub m of n is p. So when I add m to n, I should get p. Now, then this is indeed a function. This defines a relation. Why is this a function? You have to do some work here. I don't want to do it over here. You see, in this definition, like I just defined a relation. I took all m and p such that there exists a function f sub m satisfying these properties, and f sub m of n is p. That this is a function follows from the uniqueness of these guys, okay? So you have to prove that these guys are unique, and all this is done by induction. Like there exists a unique function such that blah blah happens, it's done by induction. So we can actually define addition by some work using induction. We don't really need recursion theorem, but recursion theorem allows us to do more general recursions, okay? So there exists such a function, that's the point, okay? This definition I wrote on the board, it actually makes sense. Now let's prove some basic things about addition. The first thing we're going to prove is something very easy. Indeed, I'm not even going to prove it. Now, notation. Instead of writing plus of mn, we shall write m plus n instead of plus of mn, okay? So instead of using this notation, I'm just going to use the usual addition notation. The first lemma is, if you add 0 to any natural number, you get n. Why is this the case? It's the case because, well, I just define it that way, okay? That's actually a part of the definition. Maybe I shouldn't call it even a lemma. And the second fact is, well, I'm just going to restate it. Maybe I shouldn't call this lemma. What should I call it? Fact? No, I'm going to call it lemma. And I'm going to explain why I called this lemma. For all mn and n, m plus s of n is s of m plus n. I'm just restating what I wrote over there. Now, why did I state this as a lemma? I mean, over here I defined addition like this. Here's why these are actually theorems, why these are something that are supposed to be derived. Prove that there exist such functions, define this operation. Now, this operation satisfies these properties requires it requires a couple of lines, okay? So what we are really doing is we're saying that these functions exist by some induction argument, then I'm defining this relation, and this relation satisfies those properties. So this definition I wrote here actually makes sense, okay? Now, in future, I'm not going to do this. When I define multiplication, I'm going to say that there exists such a function, blah, 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 happens, and then that there exists such a function can be proven by a similar argument like this. Anyway, the point is that this lemma holds can be proven by this construction. So I'm just going to write exercise here. I don't want to do this. Now, here's the first non-trivial lemma about addition. For all natural numbers mn, m plus successor of n is the same as successor of m plus n. Now, I know that this sounds trivial to you because this is supposed to be m plus 1, right? M plus 1 is obviously m plus 1 plus n because you think this addition is commutative. But why is addition commutative? We're going to use this lemma in the proof that the addition is commutative. So let's try to prove this just from this definition. Okay. So we proceed by induction. I think I'm supposed to give you assign an exercise, but I should do that later. Never mind. We prove this by induction. Now, this proof is not important on its own. It's some basic proof, but it's important because it kind of illustrates what you should be doing in case you need to prove an identity involving addition. Like if I ask you, why is addition associative? The proof is going to resemble the proof of this lemma. So we define addition by recursion, and that automatically forces us to prove things about addition via induction, okay? In general, if you define something via recursion, then you prove things about that thing via induction. So we're going to prove this by induction. Now, there are two variables here, m and n. So on which variable am I going to do induction? I'm going to do induction on n. What that means is this. Let n be the set of all natural numbers such that this claim holds, okay? So doing induction on n means the following. I'm letting I to be the set of all natural numbers such that this claim holds. We shall show I is inductive. Okay? Now, how do you show that some set is inductive? What does inductive mean? It means that your set is no. Remember the definition of an inductive set. It contains the empty set, namely 0, and it contains the successor of every element inside. So whenever it contains some set, it contains the successor. So I'm supposed to show two things. And then I'm going to say that by principle of induction, this is an inductive subset of natural numbers, therefore it's the whole thing. So we claim that 0 is inside this set. Why? Because if you take any natural number, let's plug in 0 here. M plus s of 0. This is, by this property, equal to m successor of m plus 0. Well, m plus 0 by the first property is m, so this is successor of m. But again, by the first property, successor of m is the same as successor of m plus 0. So m plus s of n equals s of m plus n. Okay, so 0 is inside. Now let's do the inductive step. Let m be a natural number and assume that n is an I. So let's say that this claim is true for some natural number n, okay? When I say assume that n is an I, I'm just assuming that this claim is true for some natural number n. Then, okay, what do we want to show? We want to show that the successor of n, this claim also holds for successor of n, so that successor of n belongs to this set, so that this set is inductive. Then, for all m in n, we have, let's see, we want to check that this equality holds for every m. So let's pick some m, and let's plug in s of n for n. So I have m plus s of n. Now, by the definition of addition, this is the same as successor of m plus s of n. Now let me grab some chalk from here. Where's my orange chalk? M plus s of n. Here we're using the inductive assumption, okay? We're using the assumption that n is an I. M plus s of n equals s of m plus n. Now, I'm going to use this definition again. Successor of some a plus b is the same as a plus successor of b. Okay? Now, what have I proven? M plus successor of n equals successor of m plus successor of n. This is true for all m. This means that s of n is an I because s of n satisfies this. Okay? I plugged in s of n here and it's satisfied. So, when I contains some natural number n, it contains a successor. Thus, by the principle of induction, I equals the whole thing. It's the set of natural numbers. And so, for all n and m, this identity holds, okay? Now, is this understood? As I said, this proof on its own is not important, but it's important in the sense that any identity that involves arithmetic operations on natural numbers, it's proven like this, okay? You do an induction argument. I'm just going to prove that, like in a second, addition is commutative, okay? M plus n equals n plus n. But before that, I need to give you an exercise, okay? So exercise using induction, show that for all natural numbers n, you see at this point we don't know that the addition is commutative. Which means that if I ask you what is 0 plus n, you cannot use this. You would be able to use this if you knew ahead of time that the addition is commutative, but you don't know that. So this needs to be proven. Okay? So show that this holds. The reason you can't use commutativity of addition to prove this is that we're going to use this fact to prove the commutativity of addition. Okay? Now, lemma Apparently I have a green chalk as well. For a second, like this is orange, that's green. I thought that like it was because of the angle. That can't happen, and I realized that I also have a green chalk. Never mind. So let's prove that the addition is commutative, okay? Again, like any other claim about natural numbers, this is proven by induction. We prove this by induction on. Now, there are two variables, you have a 50% chance for getting the right variable. I can try to do induction on m instead of n. Maybe it works. I don't know. When I say I don't know, I actually don't know. Like I haven't tried that. Maybe it works. But I'm going to do this, I think I'm going to go with induction on n, okay? In this case, for this case it doesn't because it's symmetric. But for some other claim, it could have mattered. It could have mattered, okay? For example, okay, in the past, like in one of the exams, I asked students to prove that addition is associative. So this was like a question. I said that assume this and this, prove that this holds. And they're supposed to do an induction. Now there are three variables. And you see, in this case, I think you should go with induction on P. But students are so used to doing induction on N, for this specific case, they try to do induction on N instead of P. And then they require that other stuff. I think it can be proven at the very end, but it requires a lot of previous steps if you choose the wrong variable to do induction with. Like for these guys, everything is symmetrical, right? Like if you interchange the places of M and N, the claim is still symmetrical, so for these cases, it's not going to matter. But for some other claims, it can actually matter which variable you choose induction for. Which variable you choose to do induction with. So we prove this by induction on n. So I'm just going to do induction on n. So let I be the set of all natural numbers n such that this claim. You have a question still? No. Such that this claim holds. Again, now I'm going to skip the middle steps. We wish to show that I is inductive and so on. Now 0 is in I. Why? Because, you see, m plus 0 is defined to be m, and at home, since for all m and n, m plus 0 is defined to be m, and you're going to show at home that 0 plus m is also m. Okay, so I'm using, over here, I'm using the exercise. The reason 0 is inside the set, it's the exercise. This is why you should prove this. Now, let m be a natural number and assume that n is an I, okay? Then, okay, we wish to show that S of n is an I. So let m be some natural number. Why am I taking such an m? Because I want to show that for S of n, something happens. Well, that something starts with the quantifier for all. For all m, something happens. So I'm just picking some m, and I'm going to try to prove that m plus S of n equals S of n plus m. Now, I start with this, m plus S of n. Now, by definition of addition, this is S of m plus n. And now, I can use you see, I don't know what to do with this. I can only use the definition, and I converted this to S of m plus n. At this stage, I know something about m plus n. I know that by the induction hypothesis, m plus n is n plus m. And now I'm going to use the definition of addition again. S of m plus m equals m plus S of m by the second property over there, okay? And now I'm going to use the previous lemma. N plus S of m equals, okay, here m and n are flipped, but I can move this successor over here by this. You see, some number plus successor of some number equals, apparently, to the number obtained by moving the successor to over here. So I can move the successor to over here by this lemma. Okay? So by lemma. And hence, what have I proven? M plus S of n is S of m plus m. And then this happens, and so S of n is an I. Thus, by induction, I equals the whole thing, and what that means is every natural number belongs to this set, which means that for every n and m, m plus n equals m plus m. So addition is commutative. Now, try to prove that addition is associative, okay? It's going to take some time, but it can be proven just like this. This is supposed to be a toy example to show you how identities about arithmetic operations on natural numbers are proven. I'm not going to prove that the multiplication is associative and it's commutative and so on. What I'm going to say is you can imitate all these proofs to prove all the identities you know about arithmetic on natural numbers, okay? So, any questions about this proof? Now, one thing you're going to realize is, when you try to prove things like this, is the following. You have to go in the correct order. You see, if I had tried to prove this via induction without proving this, at this stage I would get stuck. At this stage I need this lemma at that stage. This is why I proved it first, because I knew this ahead of time, because I prepared the notes. If you try to prove it, addition is associative, you're going to see that you will need some other identity to hold before. So you can prove all the things about arithmetic on natural, you can prove all the identities involving arithmetic on natural numbers, but you have to go in the correct order. Try to prove that addition is associative. That's an exercise, okay? Try to prove that it's associative, and you'll realize that at some point you will need some other identity. Then you have to prove that before completing the other thing. That will probably require some other identity, and at the end you're going to go back to basics, which means that you can complete the whole proof, but it's just going to take a lot of time to, let's say, prove that, for example, multiplication is distributive over addition, right? M times m plus p is m times m plus m times p. Try to prove this. It can be proven via some very long induction argument. It will stop somewhere, the proof. But you will, when you try to do that, you will have to prove a lot of other identities. That's the point. Anyway, all those are supposed to be an exercise, okay? Prove some identities involving addition and multiplication, which we're going to define in a second. Now, I'm going to erase this board. As was the case with addition, we can also define multiplication and exponentiation on natural numbers by recursion as follows. Now I'm going to define multiplication on natural numbers, and I'm going to use recursion. Here's the base case. When you multiply some number with 0, you get 0. When you multiply some number with the successor of some other number, you see this is supposed to be a binary operation. It takes 2 inputs. I'm doing recursion on the second input. So m times s of n equals m times n plus m. Now, you see, this recursion is kind of different than the previous one because, well, okay, it's not really different, but the point is I didn't just use the value of this function at the point mn. Like, I looked at m times n, but I also used addition, okay? And this is defined via some other recursion. So you can ask, like, why does this exist? You can prove via similar arguments that such a function exists, okay? This is multiplication. Now, let me define exponentiation. Now, at this point, I might get an objection for defining 0 to the power 0 to be 1. If you want, I may leave it undefined, okay? I can say that this is defined for all mn, but this is defined for m greater than 0. I can do that. But we can also say that, okay, we have a convention, 0 to the power 0 for exponentiation on natural numbers is 1, okay? Indeed, we use this convention a lot, right? You dealt with power series, right? And you use this notation. For n equals 0, you have the constant term, a0. Well, if x is 0, then you are supposed to have like 0 to the power 0. When you deal with power series, for example, you say that by convention, I'm defining 0 to the power 0 to be 1 in that specific case. Otherwise, you will have to introduce some other notation specifically designed for the constant term and so on. The point is, I'm defining 0 to the power 0 to be 1. No one can stop me, okay? I mean, you can try, but I'm going to do it anyway. What about m to the power successor of n? Again, I have this exponentiation. It takes 2 inputs, the base and the power. I'm doing recursion on the power. So m to the power s of n is m to the power n times m. So somehow we have 0 to the power 1 equals 0 to the power 0 times 0, which is going to be 0. But 0 to the power 0 is still 1. Okay? Well, this is 1. Okay? I just define it that way. As I said, if you don't like this, I might say that this definition makes sense for m greater than 0. But then I have to specifically define like 0 to the power 5, 0 to the power 4, 0 to the power 2 to be 0, and so on. This is fine. Now, let me write following, that such functions, such binary functions exist, such binary functions on natural numbers exist, can be proven by the recursion theorem, okay? By, again, a variant. The specific form of recursion theorem we proved in class, it's not sufficient. Like it doesn't directly give you these, but by some variant you can prove that these recursive definitions make sense. There are functions which satisfy these. I mean, I described you how it goes with addition, right? You first prove via induction that addition by m exists for every natural number m, and then you define a specific relation, like the relation includes m and p if f sub m of n is p, and so on. You can do similar things for these guys, which I'm not going to do because you've already seen how it's done for addition. And all the usual identities about involving plus, times, and I'm going to show exponentiation like this, just like in the computer, involving these can be proven via induction. Okay? I already told you about this, like we proved that addition is commutative. If you want to prove that, I don't know, this guy is distributive over addition or this guy is associative, prove those by induction. I'm not going to do that. You'll probably do one of those in your exam. So this is supposed to like alert all the people who were already sleeping. But this, for this lecture, apparently there are not many students like this, so I didn't have to tell you about that. But this is supposed to be a message to the students who are actually watching the video lectures. Okay, so we have 9 minutes. We defined addition and also multiplication and exponentiation, and all the identities about these you can prove on your own. You can prove in your free time. But as I said, you have to be careful. Some identities require some other identities to be proven first. So that's that. Now we're going to prove one last lemma, which gives us a characterization of well-ordered relations in terms of sequences, and then we're going to stop. Next lecture, we're going to start talking about equinumerosity. So let me erase this board. By the way, don't forget like these proofs. You see, in future, probably in a couple of weeks, I don't know, I haven't checked the syllabus, we're going to define ordinal numbers. And then the principle of induction will be generalized to the principle of transfinite induction. The recursion theorem will be generalized to the transfinite recursion theorem. And all these arithmetic operations will be generalized to ordinals. There will be ordinal arithmetic, ordinal addition, ordinal multiplication, and so on. And we're going to do similar things. We're going to, instead of doing an induction argument, we're going to do a transfinite induction argument to prove things about ordinal addition, ordinal multiplication, and so on. Okay? So what was I going to do? Oh, yes. Characterize well-ordered relations. Now, what's the well-ordered set? What's the well-ordered relation? A well-ordered relation is, don't be shy, just because the camera is recording. What's the well-ordered relation? It's a linear order relation where every non-empty subset has a minimal element. Good. Now, that's a good definition, but when you deal with well-ordered sets in real life, you'll realize that that's not the characterization you always want to use. There are other characterizations. This is one of them, which is very useful, okay? So let omega strictly less than be a strictly well-ordered set, okay? So this is a strict well-ordered relation on that set. Sorry, strictly linearly ordered set. Linearly ordered set, sorry. Then, okay. This set is well-ordered if and only if there exists no sequence omega sub I in n of elements of omega such that omega I plus 1 is strictly less than omega plus I for all I in n. Now that's the statement. Let's read this. We have a linearly ordered set, strictly linearly ordered set. This is, okay, I don't want to write strictly everywhere, but I think I have to. This is strictly well ordered if and only if there exists no sequence. Let's recall what this is. What's the sequence? It's a special kind of function. What's the sequence? Let's say with the index set n, whose elements are members of omega. This is simply a function from w to natural numbers, okay? And you denote the value of this guy at 0 by w sub 0, the value of this guy at 1 by w sub 1, and so on. So this is a function, but we use the sequence notation because... Oh, yes. Otherwise, it would be still a sequence, but its entries would be natural numbers, and its index set would be omega. It would be w. Sorry, it's the other way around. You're right. So apparently, this guy is strictly well ordered if and only if there is no sequence satisfying the following. Wi plus 1 is strictly less than wi. So I have w0. Let's say that this holds, okay, for some sequence. Then I have, let's see, w0 is strictly greater than w1. This is strictly greater than w2. This is strictly greater than w3. So a sequence satisfying this is, it's an infinite decreasing sequence. A linearly ordered set is well ordered if and only if there is no such sequence. Now let's prove this. One direction is obvious. The other direction is as well, actually. Let's prove the right to left direction, okay? I'm going to prove the contrapositive. I want to prove that if this holds, then this holds, which is the same as proving if this does not hold, then this does not hold. Or do I want to do that? No, I want to do the other thing. I want to go in this direction. I want to prove that if this is strictly well ordered, there is no such sequence. Let's prove the contrapositive. If there is such a sequence, then it's not strictly well ordered. We prove the contrapositive. Assume that there is a sequence w sub I in n, such that w sub I plus 1 is less than wi for all I in n. Then the set, let's take all these guys together. Let's put those in a single set. Now, can this set have a minimal element? No. If this set had a minimal element, by definition, it would be of the form w sub it would be of the form w sub k for some k. But then w sub k plus 1 is strictly less than that. So this set is non-empty and has no least element with respect to this relation. Thus, this guy is not well ordered, not strictly well ordered. So if you have an infinite decreasing sequence, then the sequence itself, like if you just take all the elements and look at it as a set, not as a sequence, then this guy gives you an empty set which has no least element. So your linearly ordered set cannot be well ordered. Now let's prove the other direction. Okay, I'm out of time, so I need to be quick. For the other direction, we're going to use the axiom of choice. We're going to choose elements. Okay. Now, this is that direction. Now let's go in the other direction. I'm going to prove the contrapositive again. I want to prove that if this holds, then it's strictly well ordered. Assume it's not strictly well ordered. Assume that this is not strictly well ordered. Then, by definition of not being strictly well ordered, there is a non-empty subset S of W which has no least element. Okay? Now, this is non-empty. Which means that I can choose some W0 in this. I don't use axiom of choice here. So this is like a common confusion. You don't need axiom of choice to choose one element from a single non-empty set. This is non-empty, therefore I can find something inside this. Now, let me write down the proof because we're out of time, then I'm going to explain it quickly. By recursion, define W sub I plus 1 to be the least element of, some element of this set if this set is non-empty, and I'm defining it to be W0 if this set is empty. So I'm doing a recursive definition. I'm defining W sub I plus 1 in terms of W sub I. I'm saying that this guy is defined as follows. I first look at this set, the set of elements which are strictly less than this. If this set is empty, then I'm just going to define W I plus 1 to be some element, W0. I don't care what it is. If this is not empty, then I can choose an element from this. I define it to be some element. Now, over here, this definition will look like ambiguous to you. Like, you're going to think that this is not actually a good definition because I'm not telling you which element I am choosing. I don't need to. You see, what you're doing is, if this set is non-empty, okay, take the collection of I for which this set is non-empty. Then by axiom of choice, there is a function which chooses one element from each of these guys. So when I'm saying choose some element of this, here we use the axiom of choice to find a function which selects one element from each such set, okay? So this definition looks like ambiguous, but it's not. I'm just invoking axiom of choice. I'm saying that there is a function f which chooses from these guys whenever these are non-empty. So I'm using that function. In reality, here's what I should do. Take the set of all i's such that this is non-empty. By axiom of choice, find the function which selects one element from each set, then use that function to define the sequence, okay? It's supposed to really look like this, but I don't have time. So let me be quick. Since S has no least element with respect to this relation, it can be proven via induction that w sub I plus 1 is strictly less than wi. Sorry, it can be proven that via induction that, let me call this set S sub I, okay? This is non-empty. Thus, for all I in n, w sub I plus 1 is strictly less than wi. Now, I made a definition. I said that choose one element from this set if this is non-empty, and if it's empty, I'm just choosing to be a fixed element. If I am lucky, if I'm in this case all the time, what I'm doing is I'm choosing the next element to be something strictly smaller than the previous element. But what if I'm unlucky? What if I'm in this case? Now, using induction, you can prove that we're always in this case. So this case, it needs to be written because it's a part of the definition. I'm trying to do a recursion. I'm telling you that I'm going to define it to be this guy if something happens. Well, what if not? What if we're in this other hypothetical case that you didn't include? I should also tell you what to do in that case. I don't really care what happens in this case because when you assume that this set has no minimal element, it's automatically implied that you're never in this case. You can prove by induction that because S does not have a least element, you're always in this case. Because that S has no least element with respect to that relation implies that these guys are always non-empty. So you're always in this case, meaning that you're always choosing some element at every stage which is strictly less than the element you've already had in the previous stage, okay? And that finishes the proof. I just constructed the sequence, which is, I just constructed an infinite decreasing sequence, okay? So this is a characterization of well-ordered set that we're going to use in future. Let's see. So what have we done? We learned about arithmetic operations on natural numbers, proved some basic things, and I assigned you a lot of exercises as improve various identities about addition, multiplication, and exponentiation. And we characterized strictly well-ordered sets in terms of infinite decreasing sequences. So I'll see you on Thursday.